Welcome to Delta Wings Aviation Academy, where we prepare you for takeoff.
Hello, pilots. Welcome to Delta Wing Aviation Academy, where we prepare you for takeoff. Today, we will be discussing about forward CG, aft CG in weight and balance. Fasten your seatbelts as we prepare for takeoff and get a bird's eye view of the details from the sky. Let's start. The further forward an airplane's center of gravity is, the greater the nose-down tendency it will have. Here, the center of gravity is in front of the center of lift, so the gravity pulls down and the lift pulls up, and it wants to drop the nose. And that's why we have the horizontal stabilizer to provide this downforce to keep the nose up. Now here, the center of gravity is relatively close to the center of lift, so there's a nose-down tendency, but it's not super large, and we only need a small downforce from the tail to keep the nose from dropping. But what happens if we move the center of gravity forward? It's not normally this far forward, but I'm just exaggerating it so you can see my point. Now the center of gravity is way up here. Now there's a much greater distance between the center of gravity and the center of lift, and the nose-down tendency is greatly increased. So this is going to require a larger downforce from the tail than we had before to keep the nose from dropping. A larger downforce from the tail, well, what's happened now? We have this lift pointing up, and we have the tail downforce and the weight pointing down. The total forces acting down have increased now. The weight's the same, but the tail downforce we need is increased. So it's effectively like the airplane weighs more. This is the key point here. With the center of gravity further forward, more downforce from the horizontal stabilizer is required. That means the downward acting forces have increased and the weight of the airplane has effectively increased. So if we don't want to lose altitude, we're going to have to increase the lift to balance that out. And how do we do that? By increasing the angle of attack. And this has a couple of effects. One is that we are now closer to a stall. Why? Because the airplane stalls at the critical angle of attack.
A stall occurs once the critical angle of attack is exceeded. The airflow on top of the wing breaks away, drag increases, and the lift force significantly reduces, no longer able to support the airplane's weight, which results in loss of altitude. In a stalled state, the lift vector shifts rapidly rearwards. Why does this happen? Just prior to the stall, the lift force generated by the airflow on top was focused near the leading edge of the wings. In a stall, however, the airflow above the wings no longer generates any significant lift force. Thus, the lift force vector returns to the rear. Furthermore, a higher air pressure system below the wings has an increased pushing force near the trailing edge, which contributes to the rapid shift of the lift force vector towards the rear. This shift aids in recovery from the stall due to the increased moment provided by the lift and weight couple, resulting in the nose pitching down.
So with the center of gravity further forward and this greater tail down force that's necessary, we have to increase the lift. To keep from losing altitude, we do that by increasing the angle of attack. That puts us closer to a stall. This is why an airplane with a far forward CG stalls at a little bit higher airspeed than an airplane with a further back CG. This is also why an airplane with a further forward CG cruises a little bit slower than an airplane with a far back CG. Because as the angle of attack increases, the induced drag increases. And when the induced drag increases, we're not going to cruise quite as fast. So with a far forward CG, we have a little bit slower cruise and a higher stall speed. But we also have one good thing that comes from this. The airplane is going to have a little bit better stall recovery characteristics than it would with a further aft CG. And this is because the further forward the CG is, like we said, the greater the tendency for the airplane to nose down. And well, that's how we recover from a stall. We lower the nose to reduce the angle of attack. So the airplane has more of a tendency to drop its nose and recover on its own from a stall than it would otherwise. So the airplane's going to have better stall recovery with a far forward CG. It's going to be more stable. So then with the center of gravity further aft, the distance from the center of gravity to the lift is much smaller, and there's much less nose down tendency than there was before, requiring a smaller downforce from the tail. The total downforces then are less than they were before, and we don't need to generate quite as much lift, which lets us fly at a smaller angle of attack. A smaller angle of attack is going to mean we're further from a stall, so we have more distance to go to get to a stall. So the airplane is going to stall at a little bit of a lower airspeed. And with the reduced angle of attack, we also have a reduction in induced drag, which means a little bit faster cruise. So the downside of having this aft CG is the stall recovery characteristics of the airplane are not as good. Again, the center of gravity and center of lift are now very close. And so that nose down tendency that comes from having the center of gravity in front of the lift isn't as much as it was before. And since we need to lower the nose to reduce the angle of attack to recover from a stall, we're going to have to be more aggressive about doing that ourselves by pushing the elevator forward, because the airplane is not going to nose down as much on its own as it would before. So it doesn't recover from a stall quite as well. It's also a little bit less stable, again, because the center of gravity and the lift are so close. That means it doesn't take a lot of force to move the nose up or down, right? That nose down tendency, it only requires a very small force on the tail to overcome that. So any little bump or turbulence we encounter can very easily set the nose going up or down away from its original attitude. So airplane is a little bit less stable with a far aft CG. So as long as you keep the center of gravity within its limits, the airplane is still going to be stable. It's just not quite as stable as it would be with a further forward center of gravity. So keeping the center of gravity in its limits, the aft CG, having a far aft CG might be a little bit better because you're a little bit faster, so a little bit more efficient, and the stall speed is lower. You just do need to be aware that it won't recover from a stall quite as well, and that it does still need to be within its limits, right? We have to keep the center of gravity in front of the center of lift. For your better, easy understanding, downforce that's required from the tail, which is represented by my thumb here, changes with the center of gravity location. So here, this water bottle tied to the front of the ruler is like the center of gravity. So the nose is on the right side of this airplane, and this string tied here holding the ruler up is the lift, and then my hand here is providing the downforce from the horizontal stabilizer. So with the center of gravity far forward like this, it requires quite a bit of force from my thumb to keep the nose from dropping. So that's with the far forward CG. Now, if I slide it back and bring the center of gravity right by the center of lift, now it's a very small force that my hand has to provide. So there's much less downforce on the nose because the center of gravity is further back, and we only need a very light downforce from the tail.